Hi everyone, just before I get started here, I want to thank everyone for taking a little bit of their time to listen to this presentation. I know it's not the optimal place to be presenting this, but Dr. Harper and I are really excited to have any sort of venue to show everyone what we've been working on for almost a year now, and we will be continuing doing more work on this as well. So we really are just excited to have a way to present this data and hopefully enrich you all and give you some insight into some of these amazing things going on in our own bodies. So this research was funded by the Pence Boyce Summer Research Experience, and it was a study of blood viscosity with added sodium nitrate and temperature variance, a potential therapy to regulate blood flow after induced hypothermia. Dr. Harper and I worked together through the Department of Chemistry and Geosciences to complete this research. One of the key things to understand early on when going through this project is the importance of nitric oxide for our cardiovascular health. It wasn't until very recently that we realized how important this was. The Nobel Prize was won on this in 1998 when it really was booming in the research sector. Everybody was looking at it. And it is a gaseous radical produced in the blood vessel endothelium under healthy conditions. So in people who have heart conditions or dysfunctions, likely they have an issue in the ability to produce nitric oxide. So we can see that here on the figure on the right. When we have decreased levels of nitric oxide, we start seeing thickening of arteries, inflammation, stiffening walls of the blood vessels, calcium buildup, and just in heightened blood clot risk. And we also see a correlation with age, which makes sense. We see a lot of cardiac issues in people who are older. Nitric oxide is produced by the conversion of arginine to citrulline using what is called the eNOS pathway. Just for a little background on the production of the molecule in your own body, nitric oxide deficiency has been identified as a key player in cardiac dysfunction, which is why it was looked at so closely in this study, because we're looking at cardiac arrest patients using a therapeutic hypothermia treatment. So likely a lot of these people have nitric oxide deficiency. Nitric oxide has been shown to inhibit plaque formation, which is also very interesting. So if this is introduced to someone who has a cardiac problem, it could actually provide long-term support for them as far as inhibiting further plaque formation and helping them get back on their feet. A lot of people with a cardiac problem, they end up having problems for the rest of their life, and it's just a domino effect, and it just keeps getting weaker and weaker and weaker. So any sort of way to improve their long-term survival rate is great for these patients. So these studies I looked into really highlighted what we were looking at, and they revealed what we should really be studying. So they gave me the idea for the research question. I will indicate on this that anything with quotations is something that I directly quoted from my own paper. So it's not necessarily from an article. So just so you have that information. So looking up here at the top, a study examining the blood flow to the skin noted that nitric oxide contributes 30% of the vasodilation reflex experienced in the whole body when heat is dissipated during core cooling. So this indicated to me that nitric oxide actually might be part of the key in regulating the temperature change for these patients undergoing induced hypothermia. And just in case you are not completely familiar with the induced hypothermia, it really is just cooling someone down. They can do it with ice packs or cooling blankets. They just cool you a few degrees, really, and what it does is it prevents further tissue damage. In a lot of cases, especially like in the surgical field, it gives the doctors longer amounts of time to work on a patient before traumatic bleeding or tissue damage occurs. So this indicated to us that it could possibly be something used in therapeutic hypothermia niche. Down here, in another study, scientists evaluated the amount of nitric oxide required by the body to achieve normal blood flow and discovered that patients with worse health or heart strain required more nitric oxide to propel normal circulation. So that's saying that in these patients who likely already have cardiac dysfunction, they probably need more nitric oxide. So introducing that into the system would be a benefit for them and probably necessary to promote proper circulation after these treatments. It is likely that many patients treated with induced hypothermia for cardiac arrest would have plaque, hindering their ability to produce nitric oxide. Mentioned that a little bit on the last slide, but really just saying people with this cardiac dysfunction, any sort of cardiac arrest, stroke, things that deal with problems, likely have lower nitric oxide levels. I also found several incidences where they're already using sodium nitrate for these types of treatments, at least with cardiac arrest, not necessarily with therapeutic hypothermia for a sodium nitrate. With therapeutic hypothermia, they're using nitric oxide inhalation, which is a little bit more pricey and dangerous to administer. But in other articles, I read nitrodilators were used as a blood pressure medication, essentially, in people. They relax the blood vessels. They haven't been used for extensive periods of time, so they're not really known on the market a whole lot by many people. They are safe, though. They just kind of stop working after a little while because my thought was that the body starts to produce nitric oxide properly again. Also, sodium nitrate injections have been used to prevent cardiac arrest, so they will just give you a sodium nitrate injection if they think you are about to have a cardiac event in hopes that it would reduce the chance of that occurring, and they have shown success with that. Down here in the bottom, I read this out of a research article, and it really is what made me look at this specific research project. So in several cases, it was observed that as blood was warmed, it reacts drastically due to blood shear thinning properties, leading to a turbulent blood rush. So this, to me, is the explanation for why these treatments are not working amazingly. I read several articles, and a lot of the mortality rates were around 60% for these treatments. They were not great by any means, and the explanation on most of them was, well, they already had a cardiac dysfunction, they had a heart attack or a stroke, or any number of other conditions, and they just were not strong enough to recover. But this is really saying that in the context of therapeutic hypothermia, when the blood was warmed, they're having this blood rush, and in this article they said that this blood rush would hit the brain and lead to some brain damage and just kind of shock the system. And when somebody is weak enough and you do that, they might not make it out of it. It might just be too much of a shock to their system. So the goal of this research was really to try to alleviate that blood rush. So that led us to our research question. Will sodium nitrate reduce the shear thinning stressors produced when the blood is warmed to core temperature following induced hypothermia treatment? And core temperature is just normal body temperature, so 37 degrees Celsius was the target. Some considerations we had to make is really that shear thinning of blood makes it a little bit hard to analyze it, because most fluid dynamics we work with are with Newtonian fluids. So blood is actually non-Newtonian shear thinning, which means as you put more pressure on it, it flows faster. So these layers of blood flow faster over each other, and it dramatically drops the viscosity very quickly, which in these patients is what is causing a blood rush. So it shoots the blood up into their brain very quickly, and it is just kind of a shock. So with these shear thinning fluids, you can't model them with a normal sort of model, as they have a lot of different challenges associated with them. One of the challenges is turbulence. So when they start flowing faster, these laminar sheets of flow that are normally going like this start to collide, and they create this turbulence in the sample, which is major stress on the system. And I'll analyze that a little bit in a further slide. Another major consideration we were trying to figure out how to model this blood flow was friction. So we had an ex vivo model. We could not necessarily measure the friction of the blood vessel or how the blood vessel would react to the nitric oxide signaling. So that was also a major factor in determining what we should really try to look for to model things. Shear stress was also important because non-Newtonian fluids have to be measured with shear stress included, because the amount of stress and shearing on the system affects the shear thinning of the fluid in this case. So we had to make sure we had a model in which we could measure the shear stress. So these factors all led us to the use of a Zahn-Cup viscometer, and we decided to measure viscosity of the blood as our target of analyzing flow. Essentially, they are very interconnected, and it was an easy way ex vivo to try and look at these relationships. So a Zahn-Cup viscometer is actually not a scientific tool per se. It is actually something used by paint factories to measure the viscosity of their paint before shipment. And the reason we chose that is because paint is actually a shear thinning non-Newtonian fluid as well. So we thought that if this instrument can measure paint efficiently, it should also be able to measure blood efficiently. Also, it's very user-friendly, very price-effective for our experimentation purposes. So here's a little bit more about how the blood actually reacts under these conditions of stress. So we see here on the bottom of this figure on the left, laminar flow. So laminar flow, we see that these sheets are flowing nicely with each other, and it's very uniform. And this is modeled by the Reynolds number. The Reynolds number is a measure of the inertia of the viscous forces in a fluid. And blood, when it is not warmed and it is at a normal temperature that's kept constant, has a laminar flow and is around 2000 here. So it's around this upper bound. But as soon as you heat blood, it actually begins to flow turbulently, and its Reynolds number jumps up to around here. It starts to flow like this, and all these layers start colliding, and they create these eddies in the sample, which, as you can imagine, in the blood vessel is very stressful and not good for the patient. So this is a model of what our viscosity should look like as shear rate is increased. So we can see that the Newtonian is constant over time, and with the shear thinning, the viscosity just drops dramatically as the shear rate is increased. And we'll see that model in our own data as well, and I will explain that to you and how it's occurring. So our methods, we decided to use defibrinated sheet blood. That's because it is free of anticoagulants. We wanted to make sure that our blood samples were pure, so that we added the sodium nitrate. We didn't have to worry about things like anticoagulants changing what was going on with our flow for any reason. Defibrinated sheet blood still was preserved. It still worked for the same amount of days. It's just a different method of preservation. A Zahn-Cup viscometer size 2 specifically was used to measure the viscosity. The way it's done is that this Zahn-Cup, which is just a metal cup with a hole drilled in the bottom and a hook on the top, you just lower it into the fluid. It's kind of as if you're ladling, except for your ladle doesn't just have one part of the handle. You would let the Zahn-Cup get acclimated to the temperature of your blood sample. That's because if you remember basic chemistry, if you were to put like a cold spoon into a hot soup, the thermodynamics is going to change the temperature slightly in both objects. So we wanted to make sure it was acclimated, so we knew we were getting the exact temperature each time, especially for our control curve, which was looking at a degree at a time. And then you just lift the cup out, and there's that little hole in the bottom. You measure the seconds it takes for the designated volume of fluid to flow through the orifice. And the viscometer itself comes with a equation that works to give you the viscosity using time. A warm water bath and ice water bath were used to create the temperature gradient, 1 degree at a time. A control curve was constructed from 25 degrees C to 37 degrees C. So in our experiment, 25 degrees C was used as a therapeutic hypothermia temperature. This is quite cold. It is not the normal temperature used for therapeutic hypothermia. However, it was the recommended temperature for use with our Zahn-Cup when we got it from the manufacturer. And so we decided this would likely give us good mathematical results to use it at the indicated temperature. It did say you could use it at different temperatures as long as you made a control curve. But since the purposes of our experiment were really to see how the blood reacted when warmed, we decided to go with 25. This is our lower bound, but our data was really concerned with looking at what happened when it was raised to 37. For each of the temperatures, we also tested different concentrations of sodium nitrate. So we used a 0.09 molar, a 0.1 molar, and a 0.11 molar concentration of sodium nitrate. That was really to see the correlation between, is a higher concentration of sodium nitrate releasing more nitric oxide, and is more nitric oxide creating a more even flow in the blood samples. And we did each concentration 10 different times at each temperature. We also removed major outliers in the data. So we had a indicated number of deviants for all of the samples, and if something fell out of that dramatically, it was removed from the set because it was likely due to human error, because the way we were doing these trials was by me lifting a viscometer and timing as well. So once you do 1,000 trials, you do get good at it, but there's still some level of human error that's going to be there. So really the purpose of doing 10 trials each time was to A, perfect the method so that it was consistent each time, and to try to reduce human error as much as possible. So also some calculations and definitions that really should be understood to understand how the data is being interpreted. So kinematic viscosity is the measure of viscosity in proportion to density of the fluid being measured. So this equation here came with the Zahn cup viscometer, and 3.5 and 14 were constants, and T was the time in seconds for the fluid to flow out of the viscometer. The issue with this is that kinematic viscosity is really only used by these corporations to determine if their fluid is flowing at a proper viscosity for sale. So we had to convert to dynamic viscosity, which is how the literature is looking at the comparison of blood to get proper comparison to other studies. So the only thing we had to do to get that was to multiply this calculated kinematic viscosity by the density of blood, which we gained from the literature to be 1.06, which is actually really close to water, interestingly enough. And then we also needed to find the shear rate. Like I said, non-Newtonian fluids have to be measured by dynamic viscosity and shear rate because the shearing has such a large effect on the viscosity of these fluids. So the shear rate is the velocity of blood flow divided by the height of the Zahn cup. So we got the dimensions just from the manufacturer, and the velocity of the blood flow was measured by the height of blood drop and the time. The apparent viscosity was what is really modeled in these figures that I will be showing you in the data analysis. Apparent viscosity is just a comparison between dynamic viscosity and shear rate. And the reason this is used for non-Newtonian fluids is because you cannot take the dynamic viscosity for itself because there's such a large effect on the viscosity by the shear rate. Units were calculated in Pascal seconds, so everything was converted to Pascal seconds, which is standard in the literature, and shear rate was quoted as per second. Also, it's important to note at the bottom here that normal human blood viscosity is between 3.0 times 10 to the negative third and 4.0 times 10 to the negative third Pascal seconds at 37 degrees Celsius. That'll be indicated on a lot of the figures just to give you a reference of where we're at compared to what should be occurring in the blood samples. There wasn't data on normal blood flow at lower temperatures like induced hypothermia temperatures, simply because people have not really taken a huge interest, and since the blood reacts so differently with change in temperature, it's not super clear cut through all the different studies what the normal really would be. So this is our control curve. We did this to A, see if the blood rush was occurring, and B, for comparison to our further studies to get values for what our viscosity should be at our two target temperatures. So we see a largely decreasing trend of the dynamic viscosity as the temperature was raised, which is expected as it's shear thinning and our stress is the temperature. We do see R squared value that's not very close to 1, so that shows us we don't have the most linear comparison, which indicates there's probably some turbulence in our sample, just like we thought would happen with the shear thinning. And we actually see that here. We see this dramatic decrease here, much more of a decrease from 31 to 32 than any of the other values thus far. And then it just kind of roller coasters here, and we see it just have this odd effect. And that really told us that there's got to be some of this turbulence occurring here. This is the blood rush region that these papers were talking about as the blood was flowed. And it's right here where it's being warmed right up to core temperature. And the interesting thing is that in the normal temperatures that are target for reduced hypothermia starts around 32 degrees. So usually these people are having this turbulent flow constantly in these degrees of temperature. So here's the apparent viscosity control. So that is just the data from the previous slide, but we're looking at the dynamic viscosity in this case versus the shear rate. We see a much closer R squared to 1 showing a linear relationship. This data really is going to be used in our comparison for the sodium nitrate trials to see how our apparent viscosity has changed based on our addition of the sodium nitrate into the blood. So at 25 degrees Celsius, here's our comparison of our 3 concentrations. This yellow line is indicative of our 0.09 molar, the black line is the 0.10, and the blue triangle, maybe that's like a gray color or blue, depending on what you think, is our 0.11 molar. We see with all of these, we have a much closer linear trend than the last apparent viscosity for the control. We have 0.99 in 2 of these and 0.97, which is very close to 1. And we also see many of these data points are going right through this normal blood, human blood range over their trek on the graph. So that is a very good indication that there's not a lot of turbulence. We're also in the normal range. That's to be expected at 25 degrees Celsius because it's lower temperature. We're not seeing the shear thinning effects yet. Also, just for your reference, for these graphs, there's 3 data points. The lowest just indicates the minimum gotten out of the set of 10 trials. This upper bound is the maximum gotten from the 10 trials. And then these points in the middle here are just the averages taken. And as I mentioned before, outliers, extreme outliers were removed from the data. At 37 degrees Celsius, we see that some of these ranges are more stretched out, but we also see much better R squared values than even the previous trial. They're 0.999 here, 0.99 for all of them for these different sodium nitrate trials. The control, while it was still fairly close to 1 at 0.91, not half as close as these. These are very close linear relationships, showing not much turbulence in the samples. Also, in comparison to this last graph, which I can go back for a second, we see some of these points are not 100% looking linear with each other, like the computer could not make a very defined line. But in 37 degrees, you see that these are all looking very related. The line is going straight through them. You also see multiple points in the normal range for some of these instead of just the average, which is really great. We see that a majority of their length is also going through the normal range, which is also indicative of good viscosity, non-turbulent samples. Then we compared the change in 25 degrees to 37. These data points are just the averages in this case, rather than having the complete maximum minimum average range as the other graphs had. Here, this circular marker indicates the control, which has a very steep slope in comparison to the sodium nitrate trials. And we also have this control normal box. So this is our normal blood, human blood expected value. And you can see that a majority of all of them are within this box, which is really amazing. It's showing us we're staying where we should be. And since these slopes are so flat, it shows us we're not having a dramatic shear thinning change in the viscosity where it's just decreasing dramatically. We even see with this 0.11 trial that the slope is completely flat. It stayed the same for both of these. The average was the same at 25 and at 37. We also see very little change in the 0.09. The 0.10 is a little bit odd. It went down out of the range. It's the only one out of the sodium nitrate trials that did that. And it also isn't located where we would expect it, which is between these two. And that was really hypothesized to be due to our blood was very close to expiration when that trial was run. We suspect that might have had some effect on that viscosity at the end, because a lot of our red blood cells were likely lysed at that point, and we just did not have the funds to buy more blood and do that again. So that could be a reason. We would have to do more trials to determine if that's the issue. Even though that 0.1 molar is not within where we expected it to be, it is still showing mediation. The slope here is much less steep than with the control. So that shows us all of our sodium nitrate trials are showing at least some amount of normalcy, and they're reducing this turbulence and they're flowing more normal, producing less of these shear thinning effects over the temperature change. Here's a table to just give some more defined numbers to these relationships. Something I'd highlight is the change in dynamic viscosity over the two. So these are just comparing the sodium nitrate to the control. Had a change of 0 between the two temperatures for 0.11, which is just crazy that it had no change. We completely blocked those shear thinning effects with the sodium nitrate treatment. And then we also see the 0.99 or the 0.09 and the 0.10 had a 10 to the negative fourth change compared to this 10 to the negative third in the control. So these had a much lower change of like a whole magnitude less than the control. The slopes, all the changes between those over time compared to the control were fairly similar with a very low magnitude. The change in dynamic viscosity, just looking at the beginning point at 25 degrees Celsius, we saw less change between the dynamic viscosity of the controls from the others compared to the 0.09 and the 0.11. But that also could be part of that mistrial going on, because we see that it's a little bit lower than expected here in this graph. So that accounts for that number. The dynamic viscosity at 37 degrees, the change in it compared to the slope, we see that they're larger here than in many of the other comparisons that are 10 to the negative fourth. And that's because really that mediation is being shown at 37 degrees Celsius. It's really, really low here for the control compared to these. So we're really seeing a great change in how much it's really increasing that or decreasing that viscosity with the temperature change. So some analysis of these results. At both tested temperatures, the dynamic viscosity for the 0.09 molar trial stayed within the range of normal human blood viscosity, which was shown on that graph, which is very promising for this study. If we were seeing these results and they weren't within the normal range, even if they were being kept constant, it still wouldn't be an ideal therapy, because we're still changing the system and not promoting a homeostatic environment. For the 0.10 molar, the dynamic viscosity at 25 degrees Celsius was within the range for normal human blood viscosity, but then it went outside of the range for 37 degrees Celsius. We saw that it went out of the box there. We do think part of that could have been error, but we're not entirely sure at this point. We would have to do some more work to determine if that was really going on. The 0.11 molar trial expressed the greatest amount of mediation, and it had an unchanging dynamic viscosity over the two trials, which was just astounding that it was a change of 0 over the two different temperatures. And I just highlight that overall, all of these trials, it did show that it did not allow the temperature to decrease the blood as dramatically as in the control. So the sodium nitrate did show some effect for all of the trials, even the 0.01 molar. So some limitations and improvements. I did explain a little bit of the limitation when we were going over the experimental design, but just to touch again, we were only able to use an ex vivo model, which was obviously not ideal. We can't see how nitric oxide is really affecting the blood endothelium, the blood vessel endothelium. And our Zahn cup also is not the most precise instrument. It's used in paint factories, obviously. It was great for the purposes of our experiment, and it was very cost effective, but we would definitely want to redo this data with some something more precise and something that's modeling what's going on in vivo a little bit better. The methods were also reliant on me being very consistent with the way I was rising the blood, the viscometer, sorry. So that there's always going to be a level of human error. I did do it so many times that I got very good at it, but it would be better to have something that's not as human driven just to keep consistency. Also, we were subject to a strict time frame because we had a limited amount of time before the blood expired and before all the red blood cells lysed. So that is also something to keep in mind. We also did not have a method for determining exactly how much nitric oxide was released in the samples. So we are not very sure whether the 0.11 really showed that an increased concentration of sodium nitrate was more beneficial to keeping the viscosity constant, because we don't really know how much was released. There could be a saturation point in the blood where you just can't take any more in. So we would really have to do more to determine if that's really what's going on. So some concluding remarks. Due to the results of the 0.1 molar trial, we cannot with confidence say that the sodium nitrate reduced the shear thinning effects. It did show some positive correlation, but that data was just out of the expectancy that we had. So we wouldn't want to say for sure that this is a good treatment and that this is really what's going on. We also can assay the nitric oxide to determine how much is being released. So that's another point where we're a little unsure. So we would definitely want to go on with some future experimentation to determine maybe better what's going on in those cases. Many other studies have done nitric oxide introduction with inhalation. It's a little bit more costly, and the tanks of nitric oxide are a little unstable to be brought into the clinical setting, which has been outlined in the literature. But something I saw when I was doing the analysis, I went back through many, many reports, and I started to see some very interesting things where they were doing these nitric oxide treatments in cardiac arrest with therapeutic hypothermia in mice, and they really were only seeing improved results in the first 3 hours of the time of treatment. And I thought that was really interesting that it was only helping for a specified amount of time. And then they were looking at between the control group and the mice treated with nitric oxide, and there was not much difference at all in the mortality rate and improved survival over time. So that kind of got me wondering what's really, really going on here, and maybe there's more to be uncovered in this research. Well, of course there is. But I really want to highlight here that this research experience did not stop with this experiment for me. It really kept me going. I did more research, I got more invested, and it actually brought me to this really interesting phenomenon where I was seeing in the literature that during oxidative stress, the pathway producing nitric oxide in the body is shut down. And the real interesting thing here is that cardiac arrest is a large oxidative stress inducer. So these patients might actually have messed up all of their nitric oxide pathways in their body when they had their cardiac event. And then when we're treating them with therapeutic hypothermia, a lot of the studies weren't really indicating that that might have been a factor, that their pathways are just inhibited. So our supplementation is only going to last so long. It's not going to give them time for their own nitric oxide pathways to start producing the nitric oxide that they need. And if they need more, as indicated by that study, I mentioned at the very beginning that they need even more in a dysfunction state to properly circulate blood. It's only going to last for a few hours. I even found more, which I thought was the most interesting, that not only do these pathways, when they're broken by oxidative stress, they produce harmful reactive oxygen species, but they also scavenge the endothelium of nitric oxide, further depleting it. So they actually start using nitric oxide to produce more of these bad reactive oxygen species, which induce inflammation and bad effects and cause more stress on the system. So if we're doing a treatment where we're introducing nitric oxide, maybe it will help for a little bit because some of it is able to go and affect the proper things and promote vasodilation and angiogenesis like it should. But if we have all of these broken or uncoupled pathways, which nitric oxide pathways are enos pathways, it actually can be producing even more of these reactive oxygen species, and that's why these people are not seeing improved outcomes over time with these treatments, that it's only working for a little while and then stopping. At least that's my hypothesis. So from this research, we looked at all this data and analysis, and it led us to all of these new and interesting thoughts, and that's really illustrated as well, this uncoupled versus coupled relationship in this figure here. And I won't get into the weeds of this very much just because we're focused on the first project. But I do want to express that this experience has carried forward into even more amazing ability to do research. So in the coupled pathway, this is just reflecting what I said about the nitric oxide is produced when it's in the normal state with the arginine being converted to citrulline. But in areas of oxidate uncoupled enos, which is done by oxidative stress, we have superoxide products being made that are using nitric oxide to create peroxynitrate, which induce more oxidative stress, which just keeps this going in a infinite loop of increased oxidative stress and problems for the patient. Something to note here too is that this BH4, which is tetrahydrobutyrin, is being reduced to BH2 in this pathway. So all of this research regarding this new phenomenon I heard from the literature when I was trying to understand the analysis of these results led to a new research question. So will an introduction of tetrahydrobutyrin, that BH4, into endothelial cells recouple the enos pathways and promote proper levels of nitric oxide? And Dr. Harper and I will actually have the opportunity to test this because we have been funded by Pence Boyce again to do this research. So this presentation does not end here. You'll have to tune in a year from now or come to homecoming and see what we get out of this further experiment because we've been given the opportunity to keep working on these ideas, and it's really been an amazing experience. And I won't get too far into the details of what's going on with this project. You will have to tune in next year after it's completed. But I'd like to just make some final acknowledgements. So of course we want to thank the committee, the selection committee for Pence Boyce, who picked us for research, Dr. Harper and I. Also the Pence Boyce was our funding for the project, but for me personally as the researcher, I felt like I got so much more out of this than just funding. I was given this opportunity to work with a mentor over the summer. I learned so much about being a scientist, what research is really about. I learned how to think so much more critically than I ever was doing before this experience, and really opened my eyes and I think made me a better student. On that note, I'd also really want to thank my mentor, Dr. Harper. We've been working together for almost a year. She's the one who actually got me to apply for Pence Boyce. I was doing a smaller version of this research for her physical chemistry class, and she said, well, why don't you look a little deeper and see if we can find something to look at for this and do research over the summer. And we did. And we're even going to do a whole nother year looking at a little bit deeper into what's going on in these situations. And that's very, very exciting. We've been working together for a really long time. I'm one of her TAs, and we really, I think, work well together, and I've learned so much from her. I also want to thank the Department of Chemistry and Geosciences and the Department of Biology. These research projects have really been biochemistry focused, and I've needed the help from both departments to get everything done, help me get materials, let me use equipment. and they have been really just happy to help and made the process as easy as possible. Specifically, I also want to thank a couple other professors, so Dr. Long and Dr. Sharda. They were really happy to sit down with me and look at some of these when I was looking at the data for this experiment, and also why things worked so well. Like our data, it mediated the blood flow so well, but then it only was working for a couple hours in these mouse experiments, and it was very intriguing why it was only working for so long. Dr. Sharda and Dr. Long really just, I wanted a set of fresh eyes to look at the data, and they gave that to me, and they let me sit and talk through ideas, gave me advice, and it really helped me to become a better researcher and to think critically. It led to me coming up with this new project and all of these new opportunities that we'll get in this next year of research here, and it's just really exciting. These two professors in their classes have also made me definitely a better researcher and a better critical thinker. Then I also didn't add this on the slide because it'd just be too many people to list, but my friends who offered me support in this, it's been a really long year working and trying to analyze everything, and it's a very unique experience to have, and the support was well needed in those times. So I thank my friends and family for that. I just want to conclude here with some of my references. There are quite a lot of them, but it was a very well-researched project. And then I just invite you, if you have any questions, to email me. My email is on the slide. And also feel free to give me any comments, anything you think. I love any insight because I am learning things just as you are. I thank you again for your time and your attention. I hope you all have a great day.